This time we've got the honor to have Alexander or Sasha Vezhnevets. Did I say it correctly? Sasha?
Yes.
No. With Sasha, I met like a few years ago in the summer school, and well, now he's in Google DeepMind, working on hierarchical reinforcement learning. He got his PhD from the ETH in Zurich in machine learning, in the machine learning lab, where he worked on weakly supervised semantic segmentation. He did a postdoc at the University of Amsterdam, working on object detection and recognition. And, well, as you see, today he's going to present his latest work on feudal networks for hierarchical reinforcement learning. Let's thank the speaker.
Can you hear me well?
Yes.
Thanks a lot for this nice introduction. So my talk today will be kind of in two parts. I will start with a little introduction to deep reinforcement learning and reinforcement learning. Then I'll talk about hierarchical RL. Just to start, I want to kind of like take a step back and think a bit what do we usually think when we talk about AI? Especially, you know, like if you're talking to your auntie or maybe someone who's not in computer science, and you're like, so what are the parts of AI? What should it have? And so the people will usually say, well, it should have some kind of perception, should understand what the objects are, should be able to talk to me, should probably have some memory, something like that. And as was mentioned, like I've spent quite some time of my career in perception. And there's lots of interesting works going on in language and in memory. But I think like the key thing that is really important for artificial intelligence is something like a sequential decision making. Is for the machine to be able to act in the world, make difference to that world, change it somehow, and learn from that experience. And this is what reinforcement learning as a subject is about. So in a simple version, you can think of reinforcement learning as a game. So you have the agent represented by a human brain here. You have the world, and the game goes like that. At every tick of the discrete time, the world will show something to the agent, sort of what's going on. The agent will spit out an action. And then the world will give it a reward. And then it goes on in discrete time until until the episode is over, or maybe indefinitely, depending on the setup. And the goal of the agent is to maximize what is called return. It's the sum of all the rewards from now to infinity, or to the end of the game. Summing infinite sums are nasty objects, so what people usually do, they would put a little discount factor, constant gamma, in front of and take it to the power every time they go further, so your return, the influence of the reward further in time kind of decays exponentially. So it allows us to think about those objects in the finite terms. And what defines the agent's behavior is his policy. Policy is just a probability of emitting a particular action given the state of the world. Maybe it's memory or something like that. That's what the dots are here for. And another important object that kind of describes both the world and an agent with a fixed policy is the value function. It's the expectation of your return given a particular state. So it's a sort of a characteristic of a particular policy. So as a branch of machine learning, how does it stand compared to supervised learning, unsupervised learning? So there are a few important differences. In supervised learning, we always sort of know the answer to our question. Here, the only thing that we get from the environment is the reward, and it can potentially be delayed. I can do something now and get the reward only after I graduate from the university and pass the exams and so on and so forth. It can also be misleading. I can do something, get a negative reward, but only in a few steps I will get a really high positive reward as a consequence of what I did right now. So the supervision is not as clear as in supervised learning. Moreover, time really matters. So the rewards can be good but delayed. Moreover, as the agent interacts with the environment, it generates its own data. What I mean by that is that if your agent, for some reason, chooses to just always walk into the wall, this will be the only data it observes. If you're training a neural network on ImageNet, you always get new images, you always get good images, you always know which labels are they. Your gradient will push you back, even if your model diverged a little bit here. You're generating your own experience. You have to explore the environment, you have to find new places with potentially more reward. There's a lot of sort of in the hands of an agent. And there's of course the problem of exploration. You maybe start somewhere, your agent starts somewhere in a small part of the environment and has to actually go and explore the rest of it to find potentially better sources of reward. So it's a much more general problem, and there's a lot of very interesting topics to look at there. So as a deep learning person, when you look at that diagram, you're like, all right, I can kind of feel where can I put a neural network in here. But the question is sort of, how can I train it? So I'll briefly explain I think the easiest reinforcement learning method out there. And it's actually really a great one, and we'll use it all the time. So the intuition is, as usual in deep learning, you trust your network and you follow your gradient. So let's assume that there is a neural network or some model that parameterizes our policy probabilities, and then what we want to do is just want to climb the gradient of the expected return, right? So there's a very handy theorem from the 90s from Williams, which says that you can have an unbiased estimator of this gradient, which is just the gradient of your log policy multiplied by the return and Monte-Carlo role. So this works very simple. So you have your parameters, you have your policy, you run that policy, and you generate the experience. You get the state, you feed it through the network, it spits out an action, you get the reward, and you go on. Then you have a finite length episode. You can compute your empirical return for every step, and you can just use that gradient. That's as simple as that. You can perform gradient descent, you can feed it to a neural network. There's a slight modification that makes this thing even better, which is an actor-critic method. So as on the previous slide, the return term here has quite a strong variance. Sometimes we get a lot, sometimes we don't get anything. You can have a very spiky one. So we just replace it with the return minus the estimate of the value function. So we train a separate network to predict how good is our policy doing right now, and we get a positive gradient if we're performing better than we expected, so the return is greater than the current value function estimate, or we get the negative gradient if we did worse than we expected. And of course a little term to make that value function fit our empirical return. So this bit would be called the critic. So to make this a little bit more particular, let's look how it could look in a real architecture that you can train to play Space Invaders or whatever you really want. So let's say we have a frame coming in, we have a convnet, maybe we fit it output for like a fully connected layer and into the LSTM, which also knows its previous state, right? So we'll have that network spitting out the policy and the value function estimate. So from that policy we can sample an action, we can get the reward, and we can go on. This is the unroll of an episode. Let's say it was just 3 steps, right? So now we have the rewards and the value function estimate. What we can do now is we can, for every step, like for step 0, the return is the reward at the first step, rewarded gamma by the reward at the second step, gamma squared at with the reward for the third. And then we can do this trick. We can kind of, although the game might go on further, we still want to do a backpropagation from time through time now. We just like plug in the value function estimate, because that's our expectation of our return. And now we can have the return for every step, and that would give us the gradient. We can just push back through the network and train the whole thing end to end. There is another trick to make the optimization go a little bit smoother. We can have the network parameters on some kind of a distributed server, and then we'll run multiple threads. Every thread has the copy of the parameters. It plays with the environment, it gets the rewards, generates gradients, and every once in a while synchronizes them with the server. There's a brilliant paper which describes it in detail, but it's really a very elegant and simple method. And then this stuff works, and it like really works not only on Atari, which is like a more famous result, but you can train to do a variety of things. You can train it to play racing games, you can train it to do some kind of little physics puzzles, you can train it to search a labyrinth, like a little randomly generated maze for apples and stuff like that. It's really like a very generic algorithm if you want, and there's nothing more than I described to you, plus some technical details in there. That's a convolutional net, LSTM on top, and a synchronous actor critic. Just before I kind of go further, I just want to point out that there's actually a lot more to reinforcement learning literature other than what I've touched on. There's interesting questions like off-policy learning, which is, can we learn about something, can we learn by observing the agent doing something else? There's also auxiliary tasks, like can we actually help the agent learn faster by doing something like on the side, for example, predicting whether this frame is rewarding or not. There's a question of how to help agent explore. There are also very interesting results if you have a more rigid games like a game of Go, where you really know which moves, how the moves impact the environment, and you can really build a search tree over. There's a lot of things going on. This is sort of just like the simple on policy, agent playing the game, agent learning online. But so the question is, okay, so we can do that. It seems this plays Atari, it balances a stick, and it can look for apples. Like, is it overdone? Like, is there, if it works so well, like, can we close the subject, so to speak? And there are a series of games which actually turn out to be really hard. And I think one of the most famous of them is Montezuma's Revenge. I don't know, did anyone actually play Atari where they were kids? All right, there's some, okay, cool. So I played Atari, but I didn't have Montezuma Revenge on it. It was like a Soviet Atari. It was, I had only some games, not all of them.
Tetris only. Tetris only.
No, they were, my favorite one was Draconis. Never played it since. Anyway, so the game is the following, like you control that little figure, and then you just have to go through the series of rooms. And you do it by collecting keys and opening doors and avoiding obstacles. So why is this game problematic? Well, first of all, you die a lot. So you fall from a height, you die. You step on a skull, you die. These things I think are pushing you direction, so they make you fall, you die. And then the very first reward for the agent to experience when he gets to the key, for which he has to go down, jump on the rope, jump on the stairs, do something about the skull, get here, climb up and get the key. These are hundreds of steps. And it is very hard for the agent to deal with such a delayed reward, which is also sparse and quite stochastic. Also, there's a lot of actions going on. It's very, like most of the classic methods to train on it, you can sometimes get something if you give it a lot of time and literally billions of frames to go through. When the other example is sort of a bit more different one. So imagine you have a game with memory. And if anyone has a neuroscience background, they would know a water maze task. So you take a mouse and you drop it in the pool of dark water. It doesn't like the water, so it wants to get somewhere where it can stand. And there is a platform actually hidden under the water surface, but since the water is dark, you can't see it. So one will randomly stumble around, get on the platform, and then since there are some kind of orienteers around the maze, the next time you drop it in, it will swim directly to the platform because it remembered where it is, unless it's a mouse which genes for memory, blah, 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 and so on and so forth. But it's a classic neuroscience experiment. So an agent equipped with an LSTM potentially can solve this problem. It doesn't have to remember that much. LSTM is a memory model, so it should work. But if you train it, what you'll have is it will just always circle on one radius, which gives it some reward every once in a while, but won't discover the memory. Because again, it is a kind of a long-term credit assignment problem. You have to, in the beginning, when you find the platform, you have to remember where it is, and you have to influence your policy afterwards to get back to it. It's hard. So what are the... okay.
It's out of focus, maybe.
Is there something? Oh, okay, here we go. Sorry. So one problem is that policy that we're learning is represented as a reaction. So you observe something and then you spit out an action, even though there's a little bit of memory. It's a very ugly representation to work with, because many actions are invariant. You can also jitter around a little bit and then go get the key. Is that jittering, was it essential or not? It's hard to understand for an agent. Reward signal is weak, and it is just a hard setup for a network to generalize. So when a human kind of looks at that game, he's like, well, actually, it's not that hard, right? Well, if we, for example, like, it's clearly you just have to first, get over here, then over here, like there's just a few sub-goals you have to achieve, and once you see, like, your older brother playing it, you will figure it out quite fast, right? And there were actually works that tried exactly that. I think Tejas Kulkarni, when he did a PhD with Josh Tenenbaum at MIT, that was one of his papers. They literally trained a convolutional neural network detector on a few states around here, and they would give an agent a reward every time they would detect that it got there. So they would train a little sub-agent to reach all of those sub-goals, and then another agent that kind of switches on those little guys, and they showed that you can actually learn this problem. Well, that is nice, but then you have to manually define sub-goals, work with that. And there's a kind of a chicken and an egg problem there, because like, well, where do you get the sub-goals automatically? Well, you can look at the agent that is playing relatively well and cluster his data, but if you don't have that agent, how do you train it? Well, you need sub-goals, so like it kind of becomes a chicken and an egg kind of issue. So what we would really want is to have something where we could just learn this decomposition of a problem in an end-to-end, nice, smooth way. So this is where sort of the hierarchical reinforcement learning is coming in. This is sort of the meat of the second part of the talk. So the goal of hierarchical learning at large is to extract structure from behavior and use it to learn faster, generalize better, which are kind of almost the same thing. And it can come in many guises, and you can do it in many ways, and I will talk about a very particular one and then give little pointers to the literature. So what do we expect to get out of like reusing the structure? So if we can learn, for example, temporal primitives like sub-goals or sub-policies, then we will probably help ourselves with long-term credit assignment, because if you're just going like, well, get here, and once it's there you get the next goal, then you kind of shorten the trajectory by making fewer decisions, so it's easier to do credit assignment. Probably have with memory. You can also have structured exploration. So the classic way of doing exploration in reinforcement learning is just add noise to your agent. So every once in a while, instead of doing the action that it thinks is best, it will take a random one. If I would be exploring my environment like that, I would be just convulsing on the floor in muscle jitter, right? So usually, like intelligent agent explores in a structured way. Like I, for example, if I want to explore a city, I would walk around, maybe get a bike, depending on how likely am I to get killed by cars. So all those things are kind of like all of my exploration policies are structured in all that we would like to have the same for the agents. And of course, another thing is transfer learning. So if I already have certain behavioral primitives, like I know how to pick up stuff, I know how to walk, I can reuse them to solve multiple tasks. I will generalize to new ones faster, and it can be like within one environment, there are just different tasks scattered around, or when I genuinely go to some new place. So what I will be talking about today is a particular take on learning structure and hierarchical learning, just called feudal learning. So there was a paper in the 90s, this time by Diane and Hinton, it's a great paper, I actually recommend you read it, but the idea on the kind of the basic level was that, well, let's build a hierarchical agent and as we go up the hierarchy, let the abstraction increase, like each level gets takes more and more abstract decisions, and as we go down, the temporal scale decreases. So, like the emperor of Japan, of feudal Japan, only wants to think, in maybe terms of 10 of decades, right? And just sends abstract goals to his shoguns, and then they talk to samurais, and these guys run around and do primitive actions and make things happen. This sort of, if you're into deep learning, whenever someone shows you some kind of a pyramid and there's a structure and abstraction going up, you're like, yeah, I kind of seen it somewhere. It looks like a convnet, doesn't it? And it is not unlike, the intuition is not unlike a convnet. There is an abstraction going up, right? We have pooling mechanism. We have all this. We're reducing the spatial resolution, this instead of time, this is more like space. And the hope is that if we manage to figure out how to build those structured models, how to properly do abstractions in RL, we can kind of have a similar impact on RL as convnets had envisioned. Which is definitely a sizable impact to hope for. So what our model that I'll introduce right now is called Feudal Network, fun for short. Yeah, I didn't do it on purpose. So how does it work on a sort of an abstract scale? So we will have, imagine we're in some state S. We're playing the game, and I will assume that it's some form of representation, some nice feature space that we learned with the convnet or whatever is to our liking. I will tell you how later. So there will be two parts of the network, like a two-level hierarchy. There will be a manager, and a manager will be just saying, I want to go that way. That's the part of the state space or the feature space I want to end up in a certain temporal horizon. Right? And then there will be a worker that will be executing primitive actions trying to follow the direction. And this is how they will play. The manager will be sort of a compass in the feature space, pointing where it wants to go, and then the worker will be trying to follow. So what's good about this? There's a separation of concerns. The worker is the only guy who has to care about primitive actions, and the manager is the one who has the abstract goals. So we kind of abstracted away primitive actions for the manager. Second, we can run it multiple timescales. Manager can sort of issue more of a long-term plan, and the manager can follow. So the credit assignment will be easier for him. So of course there's a question, how do we learn the state, the feature space? Well, convnets will do it for us. I'll give you a spoiler. How do we train, but the main question is, how do we train the manager to lead and the worker to follow? How do we train this kind of a two-part architecture together so that they're nice and coherent? So the first result that we have in our paper is the following. Is that if you look just at the manager and what he does, then you can write and you make a certain assumption that given a goal, he will end up in a certain state with a certain probability. So this is basically saying if the worker is competent enough and I give him a goal, I will end up roughly where I asked. Not exactly, but with a certain distribution around that point. If we make this assumption, then we can write down this policy in a transitional representation. We don't have any more primitive actions, there are none of them involved. The policy is represented in state as t, what's the probability of getting to a certain other state in t plus c steps, right? Step t plus c. And then we can write down transitional policy gradient, which is a policy gradient in this transitional formulation, which is basically, again, your critic is here, return minus value function, and then here is the is just the log of that probability distribution and take a gradient with respect to your parameters. So what we're going to do is we're going to basically make an assumption on what that distribution, if we make an assumption on what the distribution is, we can train the manager. But how do we make sure that that assumption is true? we will actually give a worker an auxiliary reward for making that assumption hold. So basically, you can think about it like this. Manager assumes that the worker is competent and will take him where he wants, and it will reward the worker for actually making that happen. So the particular distribution we assume is this one. There's some fancy name for it. But I forgot it. It's like two names with a hyphen. But like the very easy thing. There are a few important things about it. One is it is relative, so it is always conditioned on this sort of the state where you are. So it's a direction. It's like a compass rather than an absolute goal. And there are it's a cosine distance to take out the arbitrary magnitudes within the neural network. So it's more like a direction, like a compass. So and you have to fix like a certain temporal horizon at which the goals are set by the manager. So and the neural network will kind of enact it all. Looks roughly like that. I'll give you more details in the next slide. But you have a convnet. It splits in two after that. Here the manager will compute the state, like just an MLP. And then you have a manager and he spits out goals. They somehow conditions the worker with those goals. Worker spits out primitive actions. The manager is trained with transitional policy gradient. This guy is trained with policy gradients. There are no gradients being passed between the two. They only but their gradients meet at the convnet. So this is a little bit more elaborate blueprint of a neural network, if you want. It might look a bit involved, but actually there's not that much going on. There's a convnet here. There's a shared representation after which they split. Multi-layer perceptron doing the feature space. Then it's in recurrent neural network here, about it we'll talk later. Just some value functions to do the actor-critic bit, spits out the goals. And then this is the worker. The only kind of strange bit is here that might be a bit surprising. And this is the way we condition workers' policy on the manager's goal. And the way we're doing it is through what we call policy embedding. And it kind of comes from the ideas people explored before with universal value functions. Idea is the following. So we will first embed manager's goal in a small, like 16-dimensional space, say 16 for example. And then the worker will embed all of the actions in the same space, and then we'll take a product, and we'll take a softmax, and it will be the action. In some sense, the worker, what he does is he's like, well, I'm in this state, and these are the options you can take from here. These are the potential directions in the latent space we can go from. And then the manager picks one of them. You can think about it sort of in a geometric interpretation that every action is embedded into some small space, small dimensional space. And then the manager says that's where I actually want to go. And then it will be a particular action chosen. But it's important to note that if you give it the constant W, like a constant directional latent space, the actions will change. It will not be just an action repeat if you fix the W, because it's just the direction the manager wants to get to, and then it's a worker has to satisfy it, so the actions will actually flip around a lot. I'll actually have a few videos later. So another question that is there is how do we make them interact? At which frequency should we update the goals? Should we fix them for some time? How to make it work best? So there are two classic ways it's usually done when you have two recurrent neural networks and you want to kind of like have them run at different times. Or sort of you don't want to update your goal at every time because that might just be too much jitter, but you also want to like have a longer term dependencies. So one is that, okay, we could just run two LSTMs in parallel and only update the goal every once in a while. That's okay, but then we don't have the manager having this kind of ability to reason on a really long temporal scale, because we know, for example, LSTMs, they lose their memories quite fast, maybe 20 steps and it's gone. We can have another one more like clockwork RNN, where we just will only tick our manager every, say, 10 steps or something like that. So this is not so good because you have longer term dependencies. Sure, your manager will be able to remember things for quite a while, but you will not observe certain frames, you will lose training data and so forth. So what we did is a pretty simple architecture, a modification of LSTM, which we call dilated LSTM. You run several LSTM cores that share parameters, but not the states. So you have, in this case, you'll have 3 states, and then you update each one of them like with an offset, just tick, 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 and then you just pull the results. So your goals vary smoothly because you're pulling, so you can't change them drastically since there's averaging involved. But then your memory, like your gradient does big hops, and your memory is degrading slow. But you still observe all the frames and you still get all the training data. So it's a nice modification of LSTM that allows the manager to be kind of like a slow-paced machinery. So just a little bit of context before I go into the results. So hierarchical learning was looked at before, especially like one of the most important founding papers was between MDPs and semi-MDPs by Sutton, Doina, and others. And this was kind of, they defined it more in terms of, well, there are sub-policies which they called options, which are kind of the sub-programs you can call. And there's a meta controller that selects them. The main difference, and there are many works that kind of follow that. The one also from Tejas where they predefine the sub-goals in Montezuma and train them manually. They all kind of follow the same logic. The main difference to feudal networks is that in feudal networks what the sub-policies are has a semantic meaning, which is transitional distribution in the transitions in the state space, right? In the latent state space. You have some feature representation and your high level just wants to get places. Well, instead of calling just abstract sub-programs that you don't really know what they're about. There's also a lot of work on just kind of generalized value functions, just learning how to get places in the environment. And there's the bit about policy embedding is kind of inspired by these works. And there's also a lot of interesting stuff in continuous control where you could try to sort of like train a spinal cord. You train it on many tasks to move things, and then you can like get like a controller that abstracts away primitive actions of your physical body, and you can try to do more things with it. They're all very interesting papers. I hope you take a look at them later. But sort of, so I'll show some experiments. These are like boring details in case you want to reproduce them. But we basically compare to the LSTM architecture I showed you before. So, okay, so Montezuma, does it actually do something on it? And the answer is yes. So what we get is like it does learn to go quite far. It trains much faster than a regular LSTM-based architecture. So if the regular LSTM gets to maybe like the second room, this guy goes quite a bit further. It even learns the trick that if you pick up a sword and go back and assassinate one of the scouts, you get really low points for that. Yeah, but so it's a nice little one. And then we can also look at what kind of sub-goals emerge from it. And what we can do is we can see, so what, like, as it was selecting goals, you can look at each state and you can record the goal that at that state as well. You can see what states in the future do satisfy that goal best. And then every state would get a score of sort of how many other states have it as a goal. And then you will see like a few peaks over here. And they actually correspond to some meaningful decomposition, which I also use in the beginning of the slides, which like get to the stairs, get off the stairs, get the key. So it seems nice and intuitive. So we're also running a few memory tasks. The water maze that I can explain also the few interesting ones like T-maze here, like a row, like your agent, it like there's a little, it's all 3D environments, just first-person view, and it's in the maze, this T-shaped maze that's over here, and one of the objects in the left or right sleeve of the corridor will have a reward, the other one will have a negative reward. And once you pick one of them, you get the reward, and then you're back into the beginning, and you have a limited time to repeat that. So what you have to do, you have to remember which one is it, and just go back to it. The one here is that you spawn, you see an object, you step on the teleporter that gives you a little reward, and in the next room you have to pick not the object that you've seen. So you have to remember what it is, and not pick it up in the next room. So like it's a little like memory problems that are quite simple for us, but are nice to today. They also do that kind of stuff on mice as well. And so you can see that like feudal architecture learns way faster and finds more interesting solutions. For example, in a water maze, it actually remembers where things are. So we can kind of try to take a look at what's going on inside the agent, what kind of sub-policies it learns, and the easiest way to do it, we can just take the content, or to take the bottom part of the architecture, forget about the manager, give it a random goal. For example, we can just record a few flavors and take it, feed it and see what happens, right? And for example, in water maze, what we see is that its policy is to remember, first go around randomly, find the platform, remember at which radius the platform is, and then invoke a policy that does a circular search at that radius. So in this picture, these are different random sub-goals that I sampled, and they correspond to different radii. And this is sort of its trajectories on the real episode. So green is the chaotic search for the first one, and then just returning to it, all the other colors. So in this sort of the top-down view on the fully trained agent, it's like looking for the goal, can find it, pop, here we go, and then now it will return to it all the time using the learn sub policy. So these are just the sub policies, I'll skip them in the interest of time. It's also ran it on a bit larger set of Atari environments, sort of comparing to different versions of LSTM and also different versions of feudal networks. And usually the result is wherever you have long-term credit assignment, wherever you have delayed and sparse rewards, you get quite a significant boost. So let's, this is the comparison to one of the previous works, Option Critic, but I think it's not that interesting. So these are the sub-policies that the network learned on Space Invaders. And you can see that they kind of like spatially separated. One is like play on the right, the other one is play more like in the center, the other one is always play on the left. So it really found out the different modes of the game rather than action repeat or something like that. And then the full policy kind of composes them together. The same thing is on Sequest. It's a game where you have to like control the boat and shoot the enemies. And it's very similar result, like different sub-policies correspond to a different spatial position of the boat, but they also, as you're just constantly emitting the same sub-goal, but it corresponds to a particular style of playing, and then the full policy is the composition of them. So we ran also a few ablative studies to see sort of like what makes or breaks the architecture. You can, for example, have instead of a policy gradient, you can just treat that goal vector as a continuous control problem and just use the standard policy gradient method that do not make any assumptions on the distribution that the worker follows. You can also, instead of relative goals, have absolute ones. You can, in the worker, you can either give it only the intrinsic reward for following the manager, or you can mix it with a little bit of with the true reward from the environment. And what we found is that actually the most important thing is like this transition policy gradient is really important. So if you don't have if you have just a regular policy gradient there that doesn't make that assumption, a lot of games will just not take off. This is this purple line here. You can add you can add the environment reward to the worker, that's fine, that actually helps, but it still also works with just purely intrinsic reward as well. Yes, and then there's just different. I think I'm out of time.
I've got 3 more minutes.
I got 3 more minutes. So cool.
Slides.
Yeah, I do. I was just like wondering, like, what's the best way to wrap it up? So, so the question is, can we actually, if those sub-policies that we learn are meaningful, so can we use it for something else? And this is more of a kind of a slide that explores. So are these sub-policies that we learned useful? Can we use them for structured exploration? Maybe they're already used for it. So what I'm plotting here is the following. So what if you explore with, I will compare 4 things. One is I will just take a random action every time step. This is a completely random policy. Then I can take a random action and then repeat it 10 times. And this is random 10 policy. And then I can also take a random W, like a random sub policy, and play it for like 10 steps and see what happens. And I can have like a full thing playing. So what would we expect is that making random actions, random jitter, doesn't get you far, but doing random, executing random sub-policies will actually do something meaningful, get more reward, but not as much reward as playing the full, like letting the full framework work. And this is exactly what we see. So the full method, like huge performance, but taking random sub-policies is actually yielding some reward on these gains, but like just random actions, not so much. So you can use it for structured exploration. There's also, I think I'll actually skip this in the interest of time. So I want to just say thanks to my collaborators from DeepMind, from Deep Learning, and from RL Group. Simon, Tom, Nicholas, Max, David, and Koray. They helped a lot. And I'm ready for your questions.
So, all right.
You showed a hierarchy of just 2 levels.
Yeah.
Have you experimented with deeper hierarchies? Because in one of your slides you see that you can extract some features that show hierarchy of complexity, it seems. Can you use a deeper hierarchy to find abstraction levels or something like that?
Thanks. It's a really good point. So what you could do is you can sort of go further on and have like the layers of managers, each one setting the goals sort of in a longer temporal scale. And we're experimenting with that right now, but I don't have any results to show. But that's definitely one of the directions to follow, and I think you can formulate them in this way, just longer temporal scales. You can have the same way of policy embedding conditioning between them, and hopefully you'll get more benefits. Maybe you also have to go to harder environments to see the difference.
Yes?
So you showed that in some situations where you might not need this memory or the long-term, extremely long-term credit assignment situations, the feudal networks don't outperform standard methods. But what are other ways in which the feudal network situation breaks? When do you maybe not have enough goals, or when is the credit assignment too long even for this method?
So there can be definitely too long for this method, this is for sure. We can even construct, just in particular construct the cases will be hard. I think that where it really, it's not like, you usually would see that it doesn't perform maybe as well, doesn't perform as much better than a regular last name. It's where very reactive games, where it's actually really, it's not about sub-goals anymore, it's about being very precise in your act and calculating your actions, something like, you know, like very reactive games, I know, Breakout, Space Invader, something like that. And that's, there you might not need anything like this, but can you make it too long? So another thing is, kind of also goes to the multi-scale question before. One of the things also that we were able, using this architecture, we can actually unroll the network for longer, use longer propagation through time. It breaks an LSTM for some reasons, but it is fine for the for the feudal networks, but again, you have memory constraints and all that, so I think like there is still a room to push it forward in terms of like this scale at which it can do temporal credit assignment. I hope that answers your question.
Any other questions?
Are the slides online?
Potentially.
Also on the agent hierarchy,
Yeah.
it seems that different tasks have different, with different lengths, different time scales. Can you learn what kind of hierarchy you need for different tasks?
Yeah, thanks. This is a good one. So ultimately, like here, we kind of fixed the temporal scale, right? It was like 10 steps, I think. You would ultimately want to learn that. But I think there is we haven't done it here, but I think there's a good chance of doing that because you actually have enough signal. You can try to sort of steer that C parameter towards predicting like further goals away. So yeah, there's definitely room for that. Yeah.
So the other question about the hierarchical structure is the possibility of making a node work both as a manager and a worker.
Sorry, say it again.
Is there a possibility of making a node work both as a manager and a worker for a very deep hierarchical structure?
To make what as a manager and a worker?
So you have a manager and you have a worker, and
Mhm.
manager sets the goals and worker takes the goals
Mhm.
and these interactions. So if you have a deeper hierarchy,
Mhm.
where there is a worker, manager, a senior manager, so can that manager work as a both as a worker, implementing the goals for senior manager at the same time setting its own goals?
Yes, that would be one of the ways to do it, right? So you can like the worker has kind of a unique place because it is the layer of the network that spits out primitive actions, right? Somebody has to do, once you're doing that, you don't need another worker, right? But the managers can be many because they are just setting goals and they can do it at a different temporal resolution, right? And then the question is whether you can do different conditioning through them. So for example, you can say, well, I will first think of the most long-term goal, right? And then from that goal, I will figure out the mid-term goal, and then I'll figure out the short-term goal, and then I will go down to the worker. This is one way of doing it. Or you can like let them all predict their goals in parallel and just feed them all to the worker and let him figure it out. Or you can go top down. Like, you know, all I'm saying is that there's a lot of creativity that you can put into this. I personally think that probably the most reasonable way to go about it is you long-term conditions, mid-term conditions, short-term. So I'm thinking like, I don't know, like I want to get back to London, I'm going to have to go through the airport, I'm going to have to take a taxi, and then I start walking. So like this is kind of intuition.
Yes?
Have you seen if there are like evidences in neuroscience? There are like two parts of the brain, like for a manager, workers, that they act this way, that you described. Did you try to look in neuroscience literature to see if there are?
So I talked to a bunch of neuroscientists at DeepMind, but I don't think there's much of the parallels like that are so like crisp clear. I think there's a bit of there's a lot to be understood about how the brain works, and I don't think we can go down to such details as like, is there something that sets the goals and so forth. But you can think of maybe in a more simple case, you can think about the worker as your spine, right? Because you kind of, to my not very neuroscientific understanding, your main brain takes a decision like I want to start walking there, but it doesn't have to bother itself with exact, muscle tensions. So it kind of passes that to your spine, and the spine does that. So this is something along these lines. And I think there are some other works that I've cited by, there's one by OpenAI by John Schulman, and there's one by Nicholas Heath, where they kind of try to do something like that in a bit of a different way from this, where they kind of have a physical kind of body they control, and that they try to kind of separate this kind of an abstract level of control from the primitive actions, so to have something that you can like later control easier. So I think there is something there, but like, is there something exactly like that in our brain? I don't know. Yes?
Maybe a follow-up question to this, and also the previous question I asked is, you said that this method sometimes isn't really good if you have reactive games, like you need to make quick decisions. So maybe can you draw a parallel to something like reflexes, in the sense that you ignore a goal if the worker deems it unnecessary or unfitting for the situation?
So this is actually what adding the environment reward to the worker signal helps with. So you can mix the intrinsic reward for following the manager's goals and the extrinsic reward from the environment. So worker tries to kind of find the balance between the two, and that helps in the reactive game. So maybe it's along these lines. Like if the worker is getting a goal, when the manager's like, nah, okay, I kind of will follow, but I can, like, with respect to the real reward, it's better to do something this right now. Like it's really, you need to dodge the bullet now for a space invader or something like that. So there's probably, like, that's the more like experimentally backed version of it. But I think, yes, probably something like that. The point is that if the manager would also learn the temporal scale of its sub-goals, because here we're fixing it, probably that would go away. But we're not doing that yet, so it might be problematic. Like maybe if the scale is too long, your goals kind of are not that meaningful anymore. But yeah.
I also have a question.
Yeah.
Perhaps it's me overfitting to your visual examples. That could be the case, because I haven't played Montezuma. But it seems that Montezuma is a close-ended game, as in to get to the final good reward, there's generally one path. Now, if you would have multiple paths, like in open-ended games, like in more realistic games nowadays, would that create a problem with your algorithm, because it would need to average on the action space? And if that's indeed the case, would it make sense to have multiple workers exploring different territories of the action space?
So I think there are two things here. One is that your action space can be complex, and potentially it can even be very structured, like I have my left hand and my right hand and they can be doing different things. But also, that's an interesting point apart, but I think what you're referring to is also like, if there are many ways they can go about, and I have really a lot of potentials, maybe I want my manager to be multimodal. I don't want to say like, just have this is my goal, maybe you can say, well, this is one goal, this is the other, how about we maybe explore this one? This also goes back to exploration question, right? If I have a large game, a large environment, and I want to maybe like look for different things. And I think there is something really interesting here if you do make your manager like maybe more like a distribution, and then you could sample from it, and then you could explore a tree, and you can even think about something like a tree search of possibilities.
Yeah.
Like if I go here, then this happens. If I go here, then this happens. So I think that would be a very nice generalization to work on.
Right, thanks. Any other? No.
Yeah, maybe one I'm just thinking about. You have the manager feeding its policy to the worker.
Yeah.
But is there a way of the worker, like I'm just thinking of real life, that the worker can signal his problems to the manager?
So yeah, it's a good point. I think in the games that we tried, since they share the vision, like all the input, then they kind of can be both quite aware of what's going on. So maybe in this particular case, this does not come out as a problem as much, but you can definitely envision like a certain communication channel up, and you can just add a connection, right? You can, for example, allow the recurrent network and the manager just to look at what's going on with the worker. We kind of try, we obviously try like many ways of wire the network, and this is the most minimalistic setup that shows all the interesting things. I think in this environment that we tried, this doesn't seem like this is a problem, but it's definitely something to look at, because in some sense, like, I actually feel the feedback, although it's quite cerebral, but like it's still like I do know what's going on. So I think
like breaking the abstraction.
Exactly, like a little bit. So I think there is definitely something there, especially if you consider a really complex system where maybe your worker has actually access to certain inputs that the manager doesn't want to even look at. So yeah, I think it's a good point.
We have no other question. Let's thank the speaker again.